So um, we, so I guess let me just say a couple things that are going on and then talk about what's left in the semester, and then we'll get back into new material. First of all, I just noticed, I don't know how it happened, but one group of exam threes got sort of separated from, yours was one of them. And so that's a different group. But yours was one, I think. And so if you have a 0 still for exam 3, don't worry about it. Hopefully by the end of the day tomorrow, I can get those graded and entered. And besides those, we're sort of at the point of the semester where, so people ask me when I'll have this graded and that graded. And at this point, all I can really say is I'll have it all graded by the time I need to submit grades, you know what I mean? Like, I'm trying to get through it all as fast as I can, but I just have a big pile and I'm just sort of working my way through it. So, and what? Yeah, right. That's a good question. No, I'm much more, when people put pressure on me, I get much harsher in my grading. So you should try to give me as much space as possible. Yeah, that's in that pile of stuff. I'll get it done as soon as I can. And then there was one other thing grade-wise. Well, maybe not. So given that my answer to any questions you have is going to be, I'm getting them done as fast as I can, are there any questions about grading? Good. That means you understood my my preemptive answer. And then what we have left. So first we have, in lab this week, we're doing that multiple choice post-test. So multiple choice intuition post-test. And if you take that, you get 100% on lab exam 3. So that's the good news for most people that, well, you can figure out how much that's worth, but it's better than not doing it and getting a 0 on lab exam 3. That's for sure. And so that's in lab, and you can take it during lab either time this week. Doesn't matter when your lab is supposed to be or whatever. If today works for you, feel free to do it. If Wednesday works better, feel free to do it then. It'll take about half an hour. And then the only other thing we have left after that is exam 5. And you have 2 chances to take that. You don't have to tell me beforehand. You can just show up to the one that works for you. The first one is Monday, December 11th at 6 p.m. in this room. And the other one is Thursday, 12/14 at 2 p.m. One room over, 1328. Anybody have any questions about those? Okay. Who remembers what we were talking about? That's not remembering, that's just reading. So last time we started talking about the work energy principle. And the work energy principle says if you add up the work done by all the forces on a body. Who remembers what work is? That's the work energy principle. But sort of what work is energy added to the chosen object through the application of a force. You can also add energy things by putting them up against something really hot or really cold. You know, that can change the energy of things, but we're not talking about that. And you can also change the energy by bouncing waves against it. And, you know, there are different ways to increase the energy in a thing. But here specifically, we're talking about changing the energy in the chosen object by applying forces. Okay. And the energy we're talking about is essentially like related to speed. So when you apply forces to things, it has some effect on the speed, and that's how it affects the energy. So the total work is equal to the change in kinetic energy. And have we defined kinetic energy yet? Yeah. We did that. We did problems. Okay. Okay, right. So we did one problem with the guy in the elevator, I think. And so let's do another one related to, you know, the same person in the elevator. So what we did was we calculated the work done on the elevator guy by either did the work done by the force of gravity, or we did the work done by the force applied to him by the floor of the elevator. Those are the only two forces acting on him, so there aren't any other choices. I think we did gravity, right? Does that sound right? So by gravity. Oh, we did both. And then did we add them up and use the work energy principle? Oh, okay, great. Well, let's. So by gravity, by the elevator, we added those two up and calculated that since the works of those two offset each other, you add them up, you get 0. There couldn't have been any change in speed. There was no change in kinetic energy. Okay. So we saw that the change in kinetic energy was 0, or in other words, the speed stayed constant. Okay, so now we're going to do the same kind of problem. This time we're going to do one where the works done by the two forces don't offset each other. So here's elevator guy. And this time, the force of gravity his mass was 50 kilograms. So the force of gravity is 0, negative 490.5. That's the same as it was before. But last time, the force applied to his feet by the elevator was 0, positive 490, just an upward force. And this time, the force applied to his feet by the elevator is 540.5. I'm just trying to remember one that comes out nice and simple. We'll see. And that's something you can measure. You know, I mean, you could just have him standing on a scale and see what the force is. And so what's the change in kinetic energy? If these forces are applied, as the elevator rises 10 meters. If the elevator rises 10 meters, what's the displacement vector? And displacement is a vector, so it 0, positive 10, yep. And so the work done by gravity is equal to the force of 0, negative 490.5, dotted with 0, positive 10. And that's 0 times 0 plus negative 490.5 times positive 10. And so you get a work of negative 4,905 joules. So as the elevator goes up 10 meters, is gravity adding energy to the person or removing energy from the person? Removing, because it's negative. And now the work done by the elevator is equal to 0, positive 540.5. So that's the force applied by the elevator, dotted with that same displacement vector, 0, 10. And that's 0 times 0 plus 540.5 times 10. And so you get positive 5405 joules. And so the work energy principle says total work, which is negative 4905 plus 5405, which is just 500, positive 500, is equal to the change in kinetic energy. So elevator guys, kinetic energy increases by 500 joules. And if you know something about speed at one of those two instants, you can use that to figure out the speed at the other instant. So what if speed, let's say that he was at rest at the start of that motion. So then we know that the change in kinetic energy is 500, and we can write that as 1/2 times the mass of 50 times the speed at the later instant minus 1/2 times the mass times the speed at the earlier instant, which is 0. And so we have 500 is equal to 25 v2 squared So divide both sides by 25 and you get 20 is equal to V2 squared. And what's the square root of 20? 4 point. I know I've seen this number before. Okay. 4.47 meters per second. Okay, well, we can figure out pretty similar stuff using Newton's second law. We can figure out a relationship between the forces that are applied and the acceleration, right? So I think this is kind of the first time that we have to be sort of careful about what kind of problems lead us to what approach. This energy approach we can use for certain things. The Newton second law approach we can use for very closely related things. So notice when is an energy approach likely to be most useful? And the answer is when you're trying to come up with a relationship between a change in location and a change in speed. And I guess the second thing to keep in mind about this is we've done other kinds of problems where you're relating a change in location to a change in speed. Those are like kinematics problems. So you'd use this if you're trying to relate a change in location, a change in speed, and you don't have enough information to use the kinematics equations. Okay. Okay, well, so the work energy principle in general isn't that useful to us. And that's because let's see. Our equation for work depends on the force being constant over the whole time that the thing's moving. So it depends on a constant force over the entire displacement. But that's not usually how it works. I mean, if you have something going down a hill over bumps and stuff, the normal force direction and magnitude are changing the whole time. And so you can't use that dot product formula that I gave you for calculating the work. But there are some cases where we can use a simplified form of the work energy principle. And what we're heading to is the conservation of mechanical energy, a really easy way to do these calculations. But in order to use the conservation of mechanical energy, we have to define a difference between certain types of forces. So forces are either, we're going to divide all the forces in the world into either conservative or non-conservative forces. Okay, so this is conservative versus non-conservative forces. Those names don't really give you very much information about what they do. Those are just names people gave them. But what we're going to see is these conservative ones are the ones we like. And the non-conservative forces are hard ones. So I'm making this distinction. I'm making this distinction because the problems that we're going to end up doing are going to mainly be made up of these easy ones, and we'll see that the ones that are non-conservative, there'll be reasons that those aren't going to come into our calculation. Okay, so conservative forces, let's say, if a force, let's say if a force vector is defined by only knowing the object's location, let's say only knowing the chosen object's location, force is conservative. So what forces are conservative? There's a really easy answer, so I'm going to give that to you first. If you want to, so now, I'll tell you these two forces. For us, I mean, there are a lot of examples of this, but the only problems that we're going to do involve gravity and forces applied to objects by springs, spring forces. Okay, so if you want to skip all the rest of this stuff I'm going to say about conservative and non-conservative, you can just, just sit there. But here's how that works. Gary, you can leave. Okay. So let's think about first a couple of non-conservative forces. Okay, so these are forces where, so we'll say going into thinking about it, we know the mass of the object. Okay, so like we know what object is being specified. And the question is, if I tell you the location of the object, is that enough for you to tell me what the force vector is? Okay. So this stapler, let's first think about a normal force. Okay. So say that I tell you the stapler is located right there, and you know the mass of the stapler and everything. Is that enough for you to specify a normal force? At first, you might think it is, because as it's sitting here right now, well, how much is that? What's the mass of that? Like 1/10 of a kilogram or something. So let's say it's 1/10 of a kilogram. more than that. If it's 1/10 of a kilogram, then the weight is applying a downward force of 0.981. And since this isn't going anywhere, there's no acceleration, we know that the normal force has to be counteracting that. So if it's just sitting here like that, the normal force is up at 0.981 newtons. So you sort of have this first thought that like maybe location is enough. But right now, the normal force is 0.981 newtons. If I push down on it like this, it's still in the same location, but now the normal force has to counteract both the weight and the force I'm pushing down into it. Okay, so let's say I'm applying 10 newtons of force to the stapler. Now, without changing the location, the normal force is 10.981 newtons. Okay, and so that can't be a conservative force. Any questions about that? Okay, what about friction force? Is that conservative or non-conservative? That one maybe is it's a little clearer that that's non-conservative because, like for one thing, if it reaches this point as it's sliding this way, you know the friction force has to be pointing that way. If it reaches that point sliding this way, the friction force has to be opposite. So location is not enough to specify the normal force or the friction force. Let's see. What about like a cable tension? Okay, well, imagine my forearm is like a cable. You know, is the location enough to know the force that this cable is applying to that object? No, and for one thing, you know, if it gets to that location swinging slowly, the tension required is going to be relatively small. If you go a lot faster, if I was going 100 miles an hour, then that force is going to be pretty big, which is why Major League, you know, you never hear about junior high pitchers tearing ligaments in their arm, but Major League pitchers tear ligaments in their arm all the time. The faster your arm's going, the bigger the forces are that are required. Okay, so cable tension is non-conservative. Normal force, friction, those are all non-conservative. So now let's think about the two examples that are conservative. And you know, these are going to be like the important ones to us. So the first one is gravity. If I tell you the location of this object, is that enough information to know the force gravity applies? Yeah, it is. And in fact, that's even more information than we need. You know, before I even tell you where it is, you know that the force is 0.981 newtons down, right? Like if it's here, it's 0.981 newtons down. If it's here, same thing. And then, so the only question is, if someone tells you the location, is that enough for you to know the force vector? And yes, it is. So the weight is a conservative force. And then think about like, if we took a spring and we know all the characteristics of the spring, we know how hard it is to stretch the spring and how hard it is to compress the spring. And we attach this stapler to it. And then, so let's say the spring's at its resting length right here. And now I start to stretch it back, okay? It gets harder and harder to stretch. And now I say, okay, right here, is it enough information for me to tell you that we're sitting right here to know the force that that spring applies to the object? And it turns out with a spring, it is. If I pull this thing back to here, the spring force has a certain magnitude going that way. If I pull it all the way back to here and then bring it back to this location, it doesn't matter what that path was. It's still the case that, you know, we still have the same force that the springs apply to the object toward the wall. So that's sort of a special characteristic of springs. Any questions about that that distinction? Well, normal force can be a lot of, so an object can be in the same place under a lot of different circumstances and have different normal forces applied to it. If I dropped the stapler from here down to the table, at the instant it hit the table, there'd be a big normal force to keep it from accelerating through the table. If I push down on it, there's a big normal force. If I pull up on it, there's a smaller normal force than the weight. So it's just never enough information to just be given the location of an object to specify the normal force.
Okay, that makes sense.
Okay. Any other questions about that? Okay, so the reason that it's important to distinguish between these two is that conservative forces have a really useful property. Conservative forces have what's called potential energy. Let's see. So let me say, at any location, an object's potential energy can be calculated. And here's why potential energy is useful. If you calculate potential energy at the beginning and end of a displacement, then the work done by that force over the displacement is equal to the change in potential energy. Negative, sorry. The work is the negative change in potential energy. Okay, so what that means is, the whole point of this is that calculating the work done by any force in general is a hard thing to do. Okay, there are some examples where it's not so hard, but in general, we don't want to have to be calculating the work done by a force as this thing moves across the ground or whatever. When you're dealing with conservative forces, you can calculate that work really easily by just using the potential energy at the later instant minus the potential energy at the earlier instant. Okay. So here are the two ways of calculating potential energy that we're going to use in this class. So these are the potential energy functions. The first one is for gravity, so I'll call this potential energy gravitational. And it's equal to the mass of the chosen object times 9.81 meters per second squared, g, times the height of the object. And this h is with reference to some chosen zero height. So before you start working on a problem, you choose something to be your reference height. It could be like, if we're dropping something down towards the table, it could be the surface of the table, or it could be the ground, or it could be the center of the earth in some cases. You can choose anything you want. The calculation comes out the same. You just have to be consistent through the whole problem with what you're calling your zero height. And then the potential energy for a spring force, so I'll call that PE spring, is equal to 1/2 times a constant K, I'll tell you what that is, times x squared where K is the spring stiffness in newtons per meter, and X is the distance from the chosen object to its resting position. So when I talk about a spring's resting position, I'm talking about if the spring was just sitting in a drawer or something, it has a certain length that it wants to be, where it's not exerting any forces on the things around it. And so we're talking about how far the object is stretched or compressed from where it would be if the spring was its resting length. Okay. Okay, so let's, any questions about that? Let's do that elevator example again, and I'm just going to calculate work done by the gravitational force. But you're going to see, we're not going to have to deal with the dot product and all that kind of stuff. We're just going to use this potential energy function. Okay, so what's the change in potential energy as the elevator rises 10 meters? And then once we have that, we'll calculate what's the work done by gravity. So what's the work done by gravity over that displacement? All right, so the first thing we have to do to figure out the change in potential energy is we have to choose something to call our zero height. So we'll call H equals 0 at the start of the motion. It doesn't matter where you choose it, you'll get the same answer in the end either way, but so H equals 0 is starting location. Okay, so the potential energy due to gravity, I'll call it PE grav 1. So this is that the first instant at the start of the motion is the mass, 50, times positive 9.81 times the height at instant 1. What's the height at instant 1? 0, because that's what we chose as our 0 height. And so the potential energy at the start is just 0. And then the potential energy due to gravity at instant 2 is the mass times 9.81 times the height. What's the height at the end of this motion? 10 meters. And so you get 4905 joules. And so the change in gravitational potential energy is 4905 minus 0, and so you get positive 4905 joules. And so the next question is, what's the work done by gravity over that displacement? Well, work is the negative change in potential energy. And so in this case, it's just equal to negative 4905. And that's the same answer that we got for the work done by gravity using the calculation for work. The thing is, this approach works for any conservative force. And that's not true of using that dot product definition. Any questions about that? Okay. So this says that if we have a problem that has only conservative forces in it, then we can use potential energy and we don't have to use any other weird way to calculate work. Okay? But most problems have some non-conservative forces in them. And the non-conservative forces we'd still have to treat in that sort of in a complicated way to calculate the work. But there are a couple of facts that sort of bail us out on that one. There are some non-conservative forces that come up all the time that always do zero work. Okay? So here are the non-conservative forces. Always do zero work. This helps us a lot. And the reason that this happens is any force that is always perpendicular. So remember the example of the car thing going along the train tracks? And when we applied a force perpendicular to its velocity vector, there was no work done. Okay, that's generally true. So in any case where you have a force that's always perpendicular to the velocity vector, even though that force is non-zero, the work done by that force is zero. Okay, so any force that's always perpendicular to the velocity vector does zero work. And so there are just two of these, but there are two non-conservative forces that are two of the most common forces that we see in problems that always do zero work. The first one is any normal force in a rolling or sliding problem. So a normal force during rolling or sliding So say you're sliding an object along the floor. The velocity vector is going this way. The normal force is this way. So those two vectors are always perpendicular. And that's true even if this thing's on an incline or it's going over lumps. And, at any single instant, the velocity vector and the normal force are perpendicular. So the work done by normal forces is equal to zero. And that's, I might go as far as to say, that is the reason that this energy approach to problems is often useful. If it wasn't for this, calculating the work done by normal forces would be super complicated, because as the thing goes over changes in the shape of the path, the directions and magnitudes of those normal forces are changing all the time. You'd have to take that into account at every instant. But because of this, we never have to even think about it. And then the other one that is useful pretty often, maybe not quite as often as the normal force, is any cable tension when the other end of the cable is fixed. So some examples of that are like pendulums, yeah, tetherball, any kind of thing swinging around in a circular motion. In a circle. So let's think about why that is. So if you have one fixed end to a cable and the other end goes to your chosen object, then the path of the chosen object is a circle or a part of a circle. And so if the thing's moving in a circular path, the velocity vector is tangent to the path. The tension force is towards the center of the circle. And no matter where the object is in that path, those two have to be perpendicular. So the work by the cable is zero. Okay, so now I've given all the setup that we need to go from the work energy principle to the conservation of mechanical energy. So let me just show how these two things are equal, how these two, sort of ideas are really saying the same thing. And I'll give you the equation that we're actually going to use in these problems. So if the only forces that do work are conservative, they don't have to be the only forces. There can be normal forces, cable forces, because those don't do any work. But so another way of saying this, if the only forces that do work are gravity and or spring forces, and the work energy principle, it starts out by saying that the total work is equal to the change in kinetic energy. You can also write that as the total work is equal to the kinetic energy at the later instant minus the kinetic energy at the earlier instant. That's what the change means. And if there's no work done by non-conservative forces, then this work total is just the negative change in potential energies. And you can rewrite that as negative potential energy at instant 2 plus the potential energy at instant 1 is equal to kinetic energy at instant 2 minus kinetic energy at instant 1. And now just rearrange these, and you get that the kinetic energy at instant 1 plus the potential energy at instant 1 is equal to the kinetic energy at instant 2 plus the potential energy at instant 2. This is called the conservation of mechanical energy. And the reason it's called that is the kinetic energy plus the potential energy is called mechanical energy. Okay, so we spent a lot of setup time on this, but this is really the equation that we're going to be using. But it comes from the work energy principle, and it only applies if there are no non-conservative forces doing work. If there are non-conservative forces doing work, you have to use the work energy principle, and sometimes it can get complicated. But so it's called conservation of mechanical energy because what it says is take the mechanical energy at instant 1 at some instant. It has to be the same as the sum, the mechanical energy at any other instant. So mechanical energy is conserved from one instant to the next. Okay. Okay, so let me do an example of how to use this. Okay, so let's say you have this hill, and up at the top of the hill, you have a guy on a skateboard. Cowabunga, dude! I thought you would like that. Okay, so let's say this hill has a height of 10 meters. Okay. So the skateboarder starts at the top. Skateboarder. He's at rest at the top. And we're going to ignore any friction, air resistance, all that kind of stuff. To speed at the bottom. Okay, so first we have to think about whether the conservation of mechanical energy applies in this case. So what forces are acting on the skateboarder at some instant during his trip down the hill? Gravity, and then there's only one other one. Normal force, yep. So the forces are gravity, the weight. That's conservative. And then there's the normal force. That's non-conservative, but it does zero work. So we can use conservation of mechanical energy in this problem. So we can use conservation of mechanical energy. Okay, so I'm going to call instant 1 the top of the hill and instant 2 the bottom of the hill. And I'm just going to set up a little table thing to calculate everything we want. So at the top of the hill, the bottom of the hill, this is instant 1, this is instant 2. And whenever you're using gravitational potential energy, you have to choose something to be your zero height. What you want to choose is zero height. Yeah, I might as well choose the lowest point. We'll call this h equals 0. But if you chose the top of the hill to be h equals 0, then he would start with a height of 0. He would finish with a height of -10, and everything would, the calculation would give you all the same values. So it's totally arbitrary. It's just once you choose it, you have to stay with it for the whole problem. Okay, so we have to calculate the kinetic energy and the gravitational potential energy. At the top, the kinetic energy is 1/2 I forgot to give a mass for him. It turns out that the mass doesn't matter, so I'm just going to write the mass in as m, and we're going to see that it cancels out. So 1/2 times m, and then what's his speed at the top? 0, yep. So his kinetic energy at the top at instant 1 is 0. And then we have to calculate the gravitational potential energy. The formula for that is mgh, So the mass is m. G is 9.81. What's h at instant 1? 10, yep. So the gravitational potential energy is 98.1 times m. And then at the bottom of the hill, instant 2, the kinetic energy is 1/2 times the mass times the speed squared. What's the speed at the bottom? That's what we want. So I'll just leave that as a variable. So I'll just leave this as capital V squared. We have two things now going on that sort of look like variables. The thing to keep in mind in that case is that m isn't something we're trying to solve for. That's something that you assume you know, and you just keep carrying it through as the formulas as a variable. The v is what we're trying to find. So, yeah. And then the gravitational potential energy at the bottom is the mass, 9.81, times the height at the bottom. What's that? 0. So gravitational potential energy at the bottom is 0. And so now we're just adding these up and putting them into conservation of mechanical energy. At instant 1, we have the kinetic energy plus the potential energy is equal to, at instant 2, 1/2 mv squared plus 0. On this 98.1, I forgot to put the m in there. There's an m. And then you can divide both sides. So, well, what do we have? 98.1 m is equal to 1/2 mv squared. You can divide both sides by m. And so now we see that we'd get the same answer no matter what that m is. For a 500-pound guy on a skateboard, that would have to be a good skateboard, I guess, but you get the same speed at the bottom as for a 20-pound kid. And so now we have 196.2 is equal to v squared, and that gives you about 14.142, I think. 14, yeah. What? Oh, yeah. Okay. So V is equal to 14.01. Okay, 0.00 meters per second. So if you go down a 10-meter hill on a skateboard without any friction, at the bottom you'll be going 30 miles an hour. Right. So the way, and I think our intuition says that mass should matter a little bit. The way the friction affects things is dependent a little bit on the mass, and so that's where the mass dependence comes in. The friction, but so there's rolling resistance between the wheel and the ground, and there's also bearing resistance between the bearings and the axle, and those depend on mass a little bit. But if there was no friction at all, then there wouldn't be any difference at all. And you know what screws up people's intuition about this? I think one thing is the frickin' Pinewood Derby. Because in the Pinewood Derby, anybody who does Cub Scouts knows that the more mass you put on your Pinewood Derby car, the faster it goes. But that is not because of friction effects. That's because those wheels have a fairly significant mass compared to the mass of the car. And so it takes energy to spin the wheels up. And it's the relationship. So everybody's wheels have the same mass. You're not allowed to change that. And but the body of the car, you know, if you change the mass of the body of the car, you're determining how much of the gravitational potential of the energy of the car has to go into spinning up the wheels. So, yeah. So don't trust the Pinewood Derby. And actually, if you ever want to, like, if you have kids who are doing the Pinewood Derby and you want to help them cheat, it's not really cheating. It's like you want to beat the system. This is totally legal. Nail one of the wheels into the car half an inch higher than the other ones, so it just never touches the ground. Okay? And then all you have to do is spin up 3 wheels, and everybody else is spinning up 4, and the difference is huge. Oh, well, it's a Cub Scouts thing where you have a block of wood and some wheels that you nail to the car, and you turn it in, and they race it going down this little hill. So it's like it's a little tiny wooden car. But okay, let's do an example that'll take less than 6 minutes. When I did the Pinewood Derby when I was a kid, my car didn't make it to the bottom, and there was one other kid in the Pinewood Derby whose car didn't make it to the bottom. So as the last race of the day, they raced our 2 cars against each other to see which one was the winner based on who got closer to the bottom. And the other kid's car went farther, so I got last place in the whole Pinewood Derby. Yeah, exactly. Okay, so let's say this thing has a mass of 2 kilograms, and the spring has a stiffness of, let's say, 400 newtons per meter. And let's say you pull this little cart back a distance of 5 centimeters, so 0.05 meters from rest. And let it go. Okay, so what this thing is going to do is it's just going to oscillate back and forth. The middle of the motion is going to be when the spring is at its resting length. And it's also going to always be at its greatest speed right at that resting length. Because the way that works is that, so say you take this and pull it back a little bit and let it go. The spring is going to be pulling on it all the way from here until it gets to the resting length. At that point, it's going to start pushing on it, which is going to slow it down until it stops over here. Then the spring's going to push it back this way until it gets back to the resting length, and then pull it to slow it down until it, until it stops. So we want to know the speed of this cart when it reaches the spring's resting length. Okay, well, what are the forces acting on it? There's a weight force, and there's a spring force, and there's a normal force. The normal force doesn't do any work, so we don't have to worry about that. Gravity actually isn't going to do any work either if you think about the change in the height. You know, the potential energy only changes if the height changes, and the height is the same through this whole problem. So the change in gravitational potential energy is 0. The work done by the normal force is 0. So all we have to deal with is the spring. So I'll do the same thing, just set up instant 1 and instant 2. The kinetic energy at instant 1 is 1/2 times the mass times, what's its speed at instant 1? 0, we're imagining it's like pulled back and then released from rest. So 0 squared. And then the spring potential energy is 1/2 times K, which is 400. And then how far is the object from the spring's resting length? 0.05. And that's squared. So what do you get here? 0.0025 times 200. So 0.5, I think. Okay. And then when it's at the spring's resting length, on its way, cruising through the resting length in the other direction, the kinetic energy is 1/2 times the mass times the speed squared. We don't know the speed, so I'll just leave it v. So you just get v squared for the kinetic energy. The spring potential energy is 1/2 times 400. What's the distance? So we're talking about it when it's reaching the resting length. So what's x in that case? 0. It's at the resting length. So there's no distance to the resting length. And so conservation of mechanical energy says 0 plus 0.5 is equal to v squared plus 0. And so v is equal to 0.7071, right? Square root of 0.5. Plus, yes.
Yes.
Okay. Square root of 0.5 is cosine of 45 degrees. Well, I just know the cosine of 45. Okay, any questions about that?
The distance.
No, because it's squared. So you can think of it as positive or negative. Either way, you squared and you get a positive. No, that's a different reason. But that's just because all that ends up mattering is how the height changes. So it either goes down, so it either has a negative value or a positive value.